And now we move from University of Copenhagen to University of Copenhagen. So we have Nico Lang, who until recently was a postdoc there, but recently became an assistant professor at University of Copenhagen. He's also affiliated with the Global Wetland Center and the Pioneer Center for AI. Before coming to Denmark, he did a PhD at ETH Zurich with Konrad Schindler and Jan-Erik Wagner. And his research, broadly speaking, is at the intersection of computer vision and remote sensing. And with that, Nico, I leave the word to you.
Yeah, thank you very much for the introduction. I guess the mic is on, right? Yes. Great. So Christian, which is which?
I never figured out.
Okay.
You're smart.
All right. Wonderful. Okay, so I will use the 15 minutes to mainly talk about this project that we call MMEarth, where we try to explore representation learning with multimodal Earth observation data. The project was actually mainly implemented and led by Vishal, who was visiting us for half a year at the Pioneer Center in Copenhagen before he started now his PhD at Wageningen University. You see there are many people involved, and I have the pleasure to present this today. So, I think Dan already touched a bit on this. Like pre-training these deep and big models is quite a topic these days. And like now, I just realized that the term foundation model sneaked into the slides because I attended the ESA workshop last week, which was about foundation models for Earth observation data. So in some sense, our work is very much aligned with the efforts to develop some very general purpose pre-trained models. But why do we actually care about developing these pre-trained models in environmental sciences? And there are like, of course, we heard now there's like good reasons to think about efficiency and reducing carbon emissions by sharing like the huge load of pre-training and training models. But there are also some reasons that just make this a necessity. So in many applications that we actually care about, we do not even have the training data to train these models from scratch. So we talk about applications that have limited amount of reference data, but also maybe biased reference data, and applications where we cannot, maybe not like in the individual tree mapping from high resolution satellite images where we could sit down and manually annotate more training data by hand, but we would have to go to the field and actually do some field measurements. Usually this is not just easily implemented. So there are several applications, like for instance, agricultural field boundary estimation, or like yield forecasting, or even carbon flux estimation. Like these are big topics, and these are, I would say, sort of the leading efforts in collecting global scale data sets and putting together lots of data sets. And still these data sets are heavily biased to a few countries and certain regions. So we hope that by pre-training models we can sort of overcome some of these limitations. So now, Earth observation data, you might have seen this super nice illustration from ESA before. It's super rich. So we live in very exciting times to analyze Earth observation data. There are optical sensors, SAR sensors, other sensors designed for monitoring climate variables, temperature, precipitation, etc. What is a very nice characteristic of Earth observation data is that we can basically align all this data automatically because it's georeferenced, because it has a timestamp, so we can actually pair this data in a rather straightforward way. And this is what we leveraged in this project, with the goal of creating a new global scale pre-training data set, which we call MMEarth, where we pair about 12 modalities sampled around 1 million locations, such that it becomes comparable with a well-known computer vision benchmark called ImageNet. So we sampled across 4 years between 2017 and 2020, and we designed this pre-training data set to be rather focused on environmental downstream tasks, so it's balanced across the terrestrial biomes. And these are like the 2 groups of modalities that we include here. We group them by like pixel level modalities, where we get data for every pixel in Sentinel-2. So Sentinel-2 images is sort of our reference modality on which we operate. And then we also have image level, or let's say tile level modalities that are a bit coarser resolution. So we include optical images from the Sentinel-2 mission, SAR data from Sentinel-1, a bunch of globally existing land cover maps or canopy height maps, and elevation. And then we also have some coarser modalities that tell us something about the climate, for instance, temperature, precipitation statistics. And we also treat the geolocation of the data itself as a modality, and the observation date of Sentinel-2 is also included as a proxy for, let's say, seasonality when that matters. So this is just a sneak peek of a few samples, how that looks like. This is a sample from a desert region, and we can see that some of these dense modalities, pixel level modalities, are actually rather boring. There is not much happening, except maybe here in the Sentinel-1 image, which is maybe hard to interpret for us. But then the data that is at the coarser resolution, like temperature, precipitation, might still tell us something about this region, what is actually happening in the Sentinel-2 image. But then other regions look more interesting, so we start to see actually what is in all these different data layers. Okay, so now multimodal or multi, this is in many upcoming preprints and paper titles. So what does that actually mean, like multimodal representation learning? And this is, I would say, sort of my approach to try organize what is happening. And I think we should be a bit more specific about what we actually talk about. So we could use such a multimodal pre-training data set to try to learn representations that generalize across different input modalities, such that we could predict the same, let's say, task from different input data. We could talk about representations that try to combine multiple input modalities. And then we could also talk about like a multitasking approach where we focus on a specific input modality, but we would like to have it, we would like to learn a rather general representation that could be useful for several downstream tasks. And this is actually what we're going to focus on with the experimentation part here. So we focus on learning general purpose representations for the Sentinel-2 optical images, but would like to get representations that are rather general for several downstream tasks. So this is the main underlying research questions that we studied with our experimentation. How could multimodal pretext tasks impact these representations? Okay, and to start with, we based our work on these well-known masked image modeling approaches. So on the left, we see this vision transformer-based approach, and then here on the right, this is a convolutional masked autoencoder approach, which is actually what we use and base our modeling on top of this. So we would like to learn this optical image encoder, and the traditional mask image modeling approach would be to mask a random subset of the patches of this input image, and then would use a reconstruction task as the pre-training task. So we extend this by putting on top these multiple decoders for all these paired modalities and treat them simply as additional reconstruction tasks from the optical input. And the same we do for the image level modalities, where we try to then estimate, for instance, temperature, or also the month in which this image was recorded. And by doing so, we aim to learn these general representations, so we could later on use this pre-trained encoder for several downstream tasks. Okay, so how would we evaluate actually if this worked? So luckily there's at least some collection of benchmark data sets. For instance, this GeoBench version 1 provides us with 5 different, more or less harmonized downstream tasks that include some land cover classification or climate zone classification and some crop type segmentation tasks. So we simply make use of these pre-existing data sets to then see how our model will transfer to all these tasks. And as a baseline, we start with a model that was pre-trained on ImageNet with a masked modeling approach. And this is basically a few-shot evaluation. So when we start using less and less data as we go from the right to the left on 3 different downstream tasks. And the first thing we looked at is, okay, what if we simply run the masked image modeling pre-training on our satellite images? Does that already improve the performance? In some cases, it did actually, except maybe for the Eurosat approach here. And then lastly, how does the multi-modal pretext training perform? And that seems to be beneficial compared to just using the images. Okay, so then we also compared to some, a very small subset of like dedicated Sentinel-2 pre-trained models, and it compares favorably against these. So I think a more interesting question is actually how to sample the Earth. And as I mentioned before, we mainly experimented with a balanced sampling strategy across terrestrial biomes. But there were also like, first of all, the question, how many locations do we need? And should we sample less or more data? And this is an experiment we carried out with a smaller subset where we randomly sampled 100 locations instead of 1 million. But here we could see that this actually drastically deteriorated performance. Another question is how big or how much context, how big should the images be sampled? And here we like experimented with smaller tile sizes. So we went down from this 124 pixels, which corresponds to about 1 kilometer, down to 64 by 64 pixels. And interestingly, this actually performs similarly to the bigger context window. And the good thing about this is that everything runs much faster, right? Like experimentation is much easier if your image crops are smaller. So this is, I think, good news, or yeah, it's maybe a bit anecdotal, specific for this pre-training strategy. Okay, so recently, so a team from ESA and Asterix Lab ran this pre-trained model on a global sample of Sentinel-2 images to produce a global embedding map. And this is a visualization of the first 3 principal components. And yeah, at this point, that's it, what we have. But it's already interesting that we start to see some emerging structures that maybe follow somehow the climate zones, etc. So there is some structure in these global embeddings. But yeah, these are now available on Hugging Face. So this is very much intermediate computation result that is sort of handed over to the research community to build on top of this, and we don't necessarily have to recompute it ourselves. I think it's super interesting, and I guess there's quite some potential for smarter sampling of the Earth, for image retrieval, etc. I think it's a nice fundamental layer to build on top of it. Okay, and yeah, so benchmarking and evaluation of these general purpose models is quite a thing, but the problem when we start to talk about global scale applications is that, for instance, the GeoBench benchmark lacks actually spatial coverage. So it's very much focused on few regions and a few tasks, etc. So we are working now together with Lucia on this MMEarth bench project. It's like a follow-up where we would like to fill in this gap, where we would like to formulate multimodal tasks where we pair the modalities from MMEarth with downstream tasks such that we can actually start to look into multimodal pre-training to see if multiple inputs can actually reduce the ambiguity in those predictions. So Lucia has a poster, and so please go and talk to her. And it's actually a very active field, so I think there's another poster about the Pangea project, which is another benchmark collection alternative to GeoBench. So please also have a look at that if that's interesting to you. So, and with this, I want to finish. If you like to learn more about this MMEarth project or want to play with the data set or the pre-trained model, it's all available and should be now easier to use. So, yeah, thank you very much.
Yeah, thank you very much, Nico. So let's open up for questions.
On the image classification, if they are pre-trained the models, how do you deal with class imbalance?
Doing the pre-training or doing the downstream?
Downstream.
Downstream. We don't treat that like sort of in a specific way. So that is given by us from the benchmark data set.
And do you validate the different methods, like comparing afterwards, which was better representing the different category that you wanted to forecast, or?
You mean comparing to other baseline approaches?
Yeah, compared to basically geolocated, I don't know, categories. I don't know what you could be separating after you have run the model. Maybe if you want to identify one feature of the terrain, do you actually afterwards assess how better or how worse a model was? Or how do you decide how this works? I mean, after you have run it.
So after the pre-training, we basically move into a supervised learning framework, right, with limited training data. So, and our main question is, do some pre-trained models transfer better to this few supervised training samples? I'm not sure if that answers your question, but so in the end we evaluate it on labeled data, right, and see if we can learn then a task-specific model with much less training data than usual.
Thank you. Very interesting. So I see that the geolocation and the time and date are things that you predict, which presumably means that they're not inputs.
Nope.
But they will typically be inputs for Earth observation. So isn't that data that you're refusing to use that you would typically use to make the predictions?
True. But yeah, that's a very good point. I mean, I think ultimately we would like to use them during the test time as inputs and condition on it, right? But if you look at like image recognition benchmarks, our main question was, okay, can we leverage this data for pre-training to get better image recognition models? But I agree that the ultimate goal will be to actually use it as an input, and this is the follow-up work that we are looking into it with Lucia's MMEarth bench project.
So this means the existing benchmarks don't supply the geolocation?
No.
That's it. Thanks.
And that is actually indeed an issue that you, even if you're interested in starting developing something with the geolocation, it's sort of lost on the way. At least that's what I understood so far.
Okay, let's thank the speaker again.